Welcome to lecture 15 of Introduction to Supercomputing. So this lecture is at the end of the 5th week, or actually um, scheduled for the first lecture of the 6th week, although it still fits the part on parallel shared memory computing. Next time we're going into GPU acceleration. Still, this lecture is more or less self-contained. The main topic is work stealing. That's a topic that is concerned with work assignment. It has often a more limited interpretation as mapping threads to processors, but I will explain it in a more general scheduling scheduling of jobs. So, and give an illustration with Julia. In the spirit of this course, algorithms are defined by working programs. Then I was perhaps a little bit too harsh when I said that for multi-threading one cannot use Python. There is Numba. I will say something about this. I have not much experience with it, but I should nevertheless mention it. And then there is the Intel threading building blocks, which provides a very nice programming model and very effective. For the purpose of this lecture, I was almost cutting it off because it seems to be for one particular architecture, Intel, but actually it works on my M1 MacBook Air, and it works very well. So it's also more than just threading. It's one general programming model, also for GPUs and FGPAs. So in some sense, as we transition into GPUs, this topic is actually kind of nice. Okay, let's start by recalling some definitions. So we are doing parallel shared memory computing. In some sense, it's kind of pedantic because every computer has multiple cores and can run simultaneously many threads. In that context, we have the work crew model, and we distinguish between static and dynamic work assignment. So these are the two purest forms. In a static work assignment, what every processor does is set before the execution of the program. And this can be realized by simply defining which jobs every worker has to process. And one then has no communication, no synchronization. So communication, so we've seen this with MPI. So this is essentially an ideal parallel computation if you work with distributed shared memory computing. No communication overhead. In parallel shared memory, one has synchronization overhead. So one may expect an ideal speed up if everything is evenly distributed. However, such ideal distribution of the jobs is kind of very seldom. So static work assignment is typically only used in limited circumstances. Dynamic assignment, then during the execution of the program, one decides which processor executes what job. Now one can then accomplish a very nice load balancing. However, if you have very small jobs, and sometimes with shared memory parallel computing, we think of a very fine granularity. And you could also have systems with already hundreds of cores. So if many workers have to do very small jobs and they all have to get access to the same job queue, then there might be a lot of synchronization overhead. Okay, here is the distinction between tasks and threads. Task is a logical construct. Threads are typically associated with cores. So one core can often handle a couple of threads. So it takes longer to launch a thread and terminate the thread than a task. So the context of work stealing is often in scheduling of threads, which thread is mapped to what processor. So I mentioned the workroom model. The other paradigm that we have been using with MPI, with message passing, is the manager worker, where there is a hierarchy. With work stealing, there is also no hierarchy. There is no scheduler that is going to say which thread is going to be assigned to what processor, which job will be done by which task. So the concept is that when a processor or a thread is idle, it's going to steal threads or tasks from other processors. So let me try to illustrate this as a hybrid between static and dynamic work assignment. So with a static work assignment, each thread or each worker has its own queue. So that's also the case here. But at the end of this process, so if a worker is done with its queue, then it's going to look for jobs in other queues. So if there is only one job queue left in the very end, then essentially this boils down to dynamic job scheduling. So the idea is that you kind of try to combine the best of both worlds. With static, you don't have synchronization overhead. With dynamic, you have a nice balanced distribution of the work. Here we want to have as little synchronization overhead as possible and still have a very nice balanced overhead. So the idle workers, they would be idle anyway in a static work assignment. They are going to look for work. Okay, so I will illustrate this with Julia. So the complete program will be posted, but the slides should already be sufficient to get the idea. So there will be many queues generated. So this is a multi-threading application where we as a programmer, we launch as many threads as we think that we will be using, and every worker is actually mapped to one thread. So this is multi-threading, not multitasking. So to simulate the need for work stealing, there will be two types of queues with small jobs and queues with large jobs. And the workers will start processing their own queue. So we have as many queues as there are workers. We also now have as many job indices as there are workers, as there are queues. So the index to the current job that gets executed is a mutex variable, mutex standing for mutual exclusive access. This guarantees the correctness. So in a way, if there's only one worker in one queue, the mutual access actually does not incur any overhead, as there's only the ith thread that is going to ask access to this atomic int variable. And so we start with the work crew. So in a way, we have covered the work crew with Julia earlier before. So this is still a self-contained lecture, so I will give the code also for this. But here, the novelty is that when a worker is done with its queue, it starts looking for all other queues, for jobs in other queues. Okay, so this will be a very basic implementation, just arrays. So I allocate the job queue. So every queue will have 10 jobs. So they are allocated at the start of the program. There are as many queues as the number of threads. So this is set when the programmer or when the user launches the program. And the threads are the generation of the jobs. This is done in a parallel for loop. So every worker will actually generate a queue. And you can see the random number generation is for the even indexed jobs. The job lengths are 1, 2, 3. And for the odd queues, they will process jobs of the length 4, 5, or 6. So the random numbers are representing the duration of each job. So we will use the sleep to simulate the uneven distribution of the jobs. Here is an example. At the end, the sum is printed, so the sum of the jobs. And here you see indeed that the odd indexed jobs, so they are actually now assigned to the workers with an odd thread ID. So 1 and 3, they have their jobs 53, 48 respectively. And worker 2 has the lightest job queue, only 14 as the entry. Okay, so if you do this with a static workload balancing, then it will take 53 seconds to complete. But work stealing will make that the queues 1 and 3 will get also processed by workers 2 and 4. Okay, so here is the, essentially it's very similar to the dynamic work crew that we have covered, except here that every queue has its own job index. So the top statement there generates a queue of mutex variables, of variables that that only one thread can access this simultaneously. So this happens with the my job. So the description at the bottom of this slide explains what happens in this atomic underscore add exclamation point. So this is a very convenient instruction. The atomic here is to make it appear to the user is that the incrementation and the returning of the value, that's one atomic instruction. So these are of course two instructions, or perhaps even more, if one considers the getting the memory movements. Typically this should all be done in a critical section. But with the atomic type and the atomic add, this is quite convenient in Julia. Okay, so you see that every thread, every worker gets a job, and then and before executing the job that's simulated by the sleep command here, it will write a message. What also happens after, when the thread wakes up, it will assign into the ith job queue at that particular location, it will assign its thread ID. So the jobs is a shared memory array, but the my job is a unique job number. Also, the atomic ensures that every worker gets to work in a unique queue. So here, in this case, every worker has, at the beginning, has its own queue assigned. Okay, so that is very similar to dynamic load balancing, where there was one queue. Okay, let's now do the work stealing. So the code simply continues when the loop ends. So the loop ended when the my job index became larger than the number of than the length of the jobs. Here in this case 10. When the worker had done all its 10 jobs, then it's going to look for queues j, and there is this more to steal boolean variable that's initialized to true, and then in the while loop immediately interested set to false. So it could happen that there are no more queues that still offer jobs that need to be done. Then more to steal will remain false. So you see that more to steal is set to true when the my job is less than the end of the job. So that means that the worker still has to return to this queue. Yeah, so this is essentially it. So there are a lot of variations that can happen, but here I implemented this in a strictly linear fashion. So the j starts from 1, does not include the thread ID, and starts then in the second part also from the thread ID plus 1. I omitted this code, but it's very similar. It's symmetric. Here is the output, so I strongly encourage you to run this. You get a feeling of what happens. So the even jobs, they had small queues. So worker 2 is actually first done. So worker 4 is then done a little bit later. So you can see that worker 2 takes a job 4. So worker 1 really has a lot of a very large queue. So it's worker 1 is only doing job 3 at that moment. So it takes job 4. When worker 1 is done with job 3, it gets job 5. So we then have 2 workers on the first queue. Worker 4 is done. The way it is set up, it actually also goes to the queue of the first queue, the queue that's with worker 1. So that's a very basic implementation. So in a way, it's not much more complicated than dynamic load balancing, and it may dramatically reduce the synchronization overhead, especially with fine-grained parallelism and with many, many threads. So it's definitely worthwhile considering. I defined the basic the basic version, where the idle workers always start from the first job queue. And this might be desirable if the first job queue contains all the high priority jobs. However, you may not want that all the idle workers are getting involved in the first queue, because that again will have more synchronization overhead. You could have that every worker would look to its rightmost neighbor with some modulo arithmetic. So the last idle worker will go to the first queue then. That is probably a more convenient work-through mechanism. Okay, I'm halfway through this lecture. So this is a lecture on work stealing. So in some sense, this is the essence of it. I presented an implementation in Julia. It's a good exercise to do this also with oneAPI. And we have also seen the work crew model with pthreads. So these are two nice programming assignments. Okay, so to make up for my dismissal of Python in the very beginning of this sequence on parallel shared memory computing. So Python has the interpreter lock, but there are a lot of tools available, and Numba is one of these tools that combines NumPy, so it's actually going to compile the code and also parallelize it. So we may go back to this because it also is suitable for GPUs. So it's still under active development. I went to the FOSDEM conference and I saw a lecture on Numba and MPI for Pi. So it might be possible to do everything with parallel computing within the Python environment. I tried it, so it installs pip install Numba. I did it on my M1 MacBook Air, and I executed this example here. Notice the decorator, so that's the modification that needs to be done. Also notice the typing. So that is already also an improvement of Python, that one can add types. So this is the high-level Monte Carlo that we have seen before. In some sense, this two-slide interlude also fits the high-level parallel programming from the third lecture in the first week of classes. And essentially also Julia fits with this high level, although it's, of course, always in the eye of the beholder. If you have a lot of experience with Python, then this is indeed high level. Otherwise, Julia might be better if you are a MATLAB user or a Julia experience user, or as we transition now to the C++ environment with the Intel threading building blocks. So, I mentioned C++, but this tool intends to be independent of a particular compiler. The URL, which was an original URL, nowadays directs directly to the GitHub page. Here are all the advantages of the threading building blocks. It's an environment that allows very fine level, very fine granularity with multitasking, and it is based in the same spirit as the standard template library in C++. It is not C++, and although a C++ programmer should find this a very natural environment. So in some sense, it's a little bit similar to, not similar in the sense to oneMP, where one adds directives, but here one changes some little changes. Let me have here the main selling point. So the Intel threading building blocks seem to be very restricted to Intel. I'm actually not running this on an Intel. I'm running this on a MacBook M1 processor. And I was surprised that with Brew it installed. And then the threading building blocks are part of oneAPI, one application programming interface, which happens to offer one single programming model for CPUs, GPUs, and FPGAs, accelerators. So in some sense, it's quite convenient that we now introduce this when we are transitioning into accelerators. So it took a little effort. So I had experience when I was teaching this Intel threading building blocks more than 10 years ago in 2012. Then I was introducing the Intel threading blocks next to pthreads and oneMP as one of the three possible technologies that were then available. I was thinking of phasing it out, but actually it might be just the opposite. It may be that it offers a very convenient and single programming model for various technologies. So there is OpenCL, but OpenCL seems to be fading in the background a little bit. Perhaps people will disagree with me, but oneAPI worked. So all the examples were originally developed for a high-end Linux workstation, and it will still have timings for this, but everything also worked with the M1 MacBook Air. With Brew, one has to be a little bit careful where to find the includes for the tbb.h, and one has to be a little bit careful for the libraries. Where are the libraries? Here is it then. This is object-oriented, so in some sense it might be overkill, certainly if one uses just saying hello. So this is the hello world, for which one needs a class with the data attributes. Every thread has a name. So there is the private data attribute, and then there is the public function, the saying hello, which is the constructor. So when you make an instance of a worker, you give it a name. So in some sense, there is the multi-threading in Python, by the way, which also one uses the class where one defines a thread. So here the name of the class is say hello. The name of the constructor is also say hello. And what this will do, it will take the name that the user of this class gives, and it will store the name. That's then what it is. And then you can call the say hello. So that's done with the operator overloading with the brackets, and that will execute the hello message. So in a way, it looks very unnatural if you're new to object-oriented programming, but it looks very natural in the sense that if one considers a thread as a worker with its own identification number, that is a privately stored variable, and that is given, the name is given when the thread is created, when the instance of the class is created. So coming from C, so a class is very similar to the struct in C. So in C, one can actually also store pointers to functions. So one can downgrade from C or upgrade to C++. Okay, so then the main program creates a task group. And here you see that the threads are created. So with the say hello, they are made, they are born, and then the task group, they're part of a task group, they are immediately started. So one can delay this creation and the launching. So the terminology here is also spawning. There is so the main program runs within a separate thread. So there is the main thread, and that main thread needs to wait. So there is the explicit wait method that is applied to the instance of a task group. Okay, so this was our hello world. Doesn't fit on one slide, but still within the C++ world, this is quite common. Okay, and now does it actually work? How fast is it? So here I took a computationally intensive task by raising complex numbers to some large power. I take complex numbers on the unit circle. In a way, for the first project, we considered the basis of attraction of Muller's method. In the lectures, we did the Mandelbrot set. So this application is not that, this example is not that far away from the Mandelbrot set. So if we understand this example, we can start computing Mandelbrot sets, or the basis of attraction, the plots that we do with very similar things. That could be actually also the second project in this class. Okay, first the serial code, which is actually written using the C standard library, using the CMAT. So every valid C program is also a C++ program. So one can think still in the purely functional fashion, which I did. So here you see the making of a random complex number. We generate an angle and use the cosine and the sine of that angle for the real and the imaginary part of the random complex number. This to avoid overflow. So we will do a lot of computations just for testing that we are still doing something meaningful, and stay kind of at the unit circle. We just can write the numbers as a test program. And here I'm using now the more convenient C++ formatting syntax. Okay, so then the computing of the powers is defined in a function. So we are filling up an array of, given an array X, we fill up the array Y with the powers. So I wanted something that was computationally intensive, so I will not optimize, I will not compile this, and also I will not use the pow function. So here you see the kind of silly comment, pow is too efficient. So again, if you are really for performance and for good code, please use the built-in functions of the mathematical library. I'm not doing this here. Because I wanted to have something that was computationally intensive, I took arrays of size 1000, and I'm doing this with 1 million. Although you can see that you can apply this in, so there are the options, so there are the dimensions to two numbers, and then the verbose flag. So the first parameter is indeed the dimension. The second parameter, so here in this case the 1 million at the bottom run, is indeed a power. Okay, so there is the interactive use, and then the command line usage that allows for taking the wall clock times. So I did this on a computer that was purchased in 2013. The computer is still around, by the way. So it took 20 seconds for a serial run. Okay, so the main program here, we take the command line arguments. There is a fixed seed. We allocate, we do the random numbers, and then we call the compute powers. So in some sense, this is to make the lecture self-contained. So this is a standalone, functional, and completely working C program. Also a C++ program, by the way. Okay, so we have this. Now, immediately the punchline. This was executed on a 16-core machine. And you can see that here we have super linear speedup. So we have a close to ideal run, actually parallel run. So we have the high level approaches of Julia and Python, but if you really want to get the most out of your computer, I would still advocate C and C++. So that's also a little bit the message that I would like to get through. And here comes then the kicker. So this was also what led me to still advertise this one API. So I took the code that I developed 10 years ago, and developed is a little bit hard, so these are simple examples, but with very little modification. You can see here that the wall clock time goes from 16 to 2.3. And this is essentially on a 4-core machine. In a way, what happens... So I started out with the work stealing, where we as programmers define what happens. And in some sense, if you want really performance, this is not recommended. So there are tools out there that create an optimal scheduling, as is the case here. So this suggests that on, say, a 4-core or a dual-core machine, you actually have a lot more speed up than you might expect otherwise. Okay, so now is the code here. So we have to rethink, or I could actually have said we should have started right from the start with an object-oriented design. So there is a class that we call ComputePowers. So there is the input and the output. So in a way, it's instructive to show that you can see object-oriented programming as keeping the data and the functions together. So the data are now data attributes. The functions are called also methods. So you initialize. That was the same as with the say hello. So we give the input, the x, the parameters to the output space. We give this to when we make an instance of this class. So we copy essentially the input arguments. Then we can make the object, and then we can also execute it. So with the operator that is overloaded, we are going to run this blocked range construction. This looks a little bit arcane, but if you have ever used the standard template library, then you will work with this ranges which have the methods begin and end. So this is working with the iterators. So the iterator here is actually still a size underscore t, but one also works with iterator objects. So we are doing the computation of the powers. So the computation that is done here is defined in this loop. But it is a blocked range construct. So that is offered by the Intel threading building blocks. In a way, this is a little bit similar to the A-crawl threads on a range that we were using in Julia. Here we have a loop that needs to be executed, and we want to run this in parallel. And for that, we use this blocked range construction. indicating that actually the constant indicates that we are not going to change, just like with the const, with the numbers on input, we're not going to change the range while we're doing it. So it's a fixed range of numbers. All right, so here is then the blocked range. And this is where I first learned about this work stealing. So the way it gets executed is that there will be a recursive splitting happening. We've encountered this with the Fibonacci numbers, with the recursive parallel. Another exercise here would be to do the parallel recursive quadrature again. So I mentioned the Mandelbrot set as one prototype, but the powers could also be that you are running, say, the composite trapezoidal rule. And you have the parallel 4, so you need to define the compute powers, and then there is one line that changes in the main program. So you include, and you compile, of course, you have the include statements, which, by the way, I did not need to change the source code. So on the M1 MacBook with Brew, I had to look a little bit where the include files were, a little bit, and then that passed that include folder to the G++ compiler. The same with the libraries. Okay, so there is a parallel reduce. So here is the parallel, the idea of work stealing. So I learned about the idea of work stealing 15 years ago, I guess, at a conference. And one of the earliest software environments was the Intel threading building blocks then, which illustrates this blocked range. And it is a recursive splitting. And it will keep on splitting as long as there are available workers available. Okay, so this is the image that I copied from the earlier Intel threading building blocks tutorial, which is now the lower level construction. So this is mapping tasks to threads. That is essentially taken care of by the system. So it's also high-level parallel computing. We do not need to be concerned with how the scheduling happens. All right, so here is a last example that I got from the tutorial. If you want to sum a sequence of integers, so then this is already a very fine-grained parallelism. Another example, and that will come in the first exercise, is the computation of a permanent. You can think of why this could be also a very good example of work stealing. I will explain later. So here is the class to sum a sequence of integers. So the integers that need to be summed are defined when you make an instance of this class. So in the object-oriented terminology, objects are instances of classes. And you can see that that is copied into the private data part. And there is a public data element, that's the sum. So one can then immediately get the sum out of this. You see, here what is kind of nice is that we are using this blocked range. And there is one kind of intricate thing, is that every thread has, or every worker has its own local sum, but it's initialized to the global sum. So in Julia we worked with this mutex with so here the sum is a sum that actually is uh, modified by every task in this blocked range without having to worry too much. Now, of course, it would be extremely bad to use the sum instead of s. So you can say, why do you need sum? It seems, I'm sorry, why do you need s? Can't you just work with sum? But sum is a variable that is shared by all the tasks. So then you would actually see no parallelism. So you can try to do this. So in some sense, it's a high level parallelism, but you could still make some very fatal mistakes that would lead to no parallelism. So in some sense, commingling the high level constructions, here we are actually using mutexes without seeing them. Okay, so then the parallel sum. Okay, so one also needs to define the recursive splitting and then the joining. So here we do the parallel sum of a sequence of n algorithms. So this is now with the parallel reduce construction. So with the blocked range and the parallel reduce, I have illustrated two of the very commonly occurring parallel patterns. So that's another way of doing parallel computing. One looks for we have seen already data partitioning, divide and conquer methods. These things are actually now implemented, provided in an environment such as the threading building blocks and available in one single programming model that is not limited to one specific compiler or platform. Okay, so here is the last code. So perhaps I was thinking that it was over already. So here you see how the main program works. So there is still the responsibility of the user to allocate. This is done with a C construction. All right. Work stealing itself is already quite an old idea. So here you see one of the earliest references. It also appeared in this overview technical report. That's what I'm citing also over there. And then there is the tutorial. So I gave the Intel website, but there is also the earlier GitHub, the oneAPI that I mentioned earlier. Okay, a couple of exercises. So Julia is great, still a very good environment to illustrate and define algorithms. However, if you really want to get the most out of your computer and you can take the opportunity to get to learn C and C++, this is still strongly recommended. Three exercises that invite you to play with the C++ environment and also in general with the idea of work stealing. So a permanent is very similar to a determinant, but there are no efficient algorithms for this. So this is going to be n factorial, and actually a very great example for parallel computing for very computing intensive. One can say that if it's a 0-1 matrix, that you actually can see this a little bit as looking for a path in a maze. So some paths, when they have a 0 there, the term in the permanent, there is no contribution of that term and you can terminate. So you have to do a row expansion, say along the first row, but it may so happen that some of these choices may lead to very short paths. And this is an environment where work stealing is actually quite appropriate. Also, the dynamic nature of the work queues can be captured by this. Okay, I'm ran out of time. It's 50 minutes past. So this is the last lecture that we will devote in this first run on parallel shared memory computing. Next time we do the GPU acceleration. And in the second half of the course, we will consider various scientific and mathematical problems where we can apply the three different technologies that we have seen.